Yeah.
Another question. So in the box you have mortality, but in the model you specify respiration rate and predation rate.
Yeah.
So here when you say mortality, does it cover both?
Yes.
Okay. But respiration does not produce particularly organic.
Well, that kind of gets soaked up when you what am I trying to say here? When you specify those
The distribution.
yeah, that kind of gets soaked up in there.
Okay.
So I don't really worry about how much of respiration goes where versus how much of predation.
Okay.
We take the total mortality and distribute it.
Oh, okay.
Fair enough?
Mm-hmm.
Okay.
But it's also a necessity to maintain the mass balance.
Right.
Because if you had respiration, you just didn't pay attention to where the nitrogen was. So that's, I mean, it's part of why we had to do it. But you're right, you know.
Okay, what comes next? Okay, let's look at nitrification. Okay, so there's an equation. It's not exact, but there's a rough equation for nitrification. And basically, ammonium takes up oxygen or consumes oxygen to produce nitrate. So again, this is a key sink of oxygen, and you know you got to get this right. Lord have mercy. Back in 1987. We actually had a fellow come and measure these numbers for the James River, and there's a book somewhere with a chapter on that, you know. You won't find a lot of nitrification measurements, and truthfully, it's a model calibration parameter, you know. But in any event, two things impact nitrification, three things. The availability of oxygen. All right, if there's no oxygen, you can't nitrify. The availability of ammonium, right? If there's no ammonium, you can't nitrify, and temperature. So this is a function that combines these rectangular hyperbola, which occur everywhere in models, right? And what this one says is if there's a half saturation constant dissolved oxygen, at KHONT, the nitrification rate is halved. If the oxygen greatly exceeds the half saturation, this is about unity, and there's no influence of oxygen on nitrification. If the oxygen is zero, then there's no nitrification. Similarly, over here you get a rectangular hyperbola that says that this is the half saturation constant of ammonium. If there's abundant ammonium, this thing becomes zero and you get a maximum rate. If there's not a lot of ammonium, if there's abundant ammonium, this becomes unity and you get a maximum rate. If there's no ammonium, you get zero. So there are two rectangular hyperbola, and it looks sort of like that. This is the ammonium, and as I said, as the ammonium increases, the rate of nitrification increases, and this is oxygen, and as oxygen becomes unavailable, the rate of nitrification decreases.
You use in the documentation here F of T. Is it the same F of T that we have seen in other equations, or is
it's the same.
It is, so there's one F of T.
And for ammonium, we actually include, I believe we have a maximum temperature of nitrification. The shape of the F of T curve for...
Oh, it's not the same for all the parameters.
But the same for all parameters. You mean the numbers in it, or the shape of it, or...
The shape of the function.
It's not.
It's not. So each parameter has its own F of T.
That's correct.
Okay.
For ammonium, there's an optimum temperature for nitrification. I forget what it is at the moment. I won't go in that. But it's shaped like that algae one, you know, like many of them are exponential. They just, as temperature goes up, the rate goes up. But that one is shaped like, long ago and far away, like about 1987, we did a lot of work with nitrification, and the shape of that curve, this function, is more or less based on that work. You know, this model, I don't know if you can see it here, but this model is more or less differentiated from a lot of models. The nitrification rate is a first order constant times the ammonium concentration. And what you see here is that this will max out. You know, it's not just the more ammonium you have, the more nitrification you get. And the theory behind that, which goes back a long time, is that, you know, this requires bacteria, and the bacteria require sites, if you will. And, you know, eventually you get to a place, no matter how much ammonium you have, the bacteria only can do so much. So this thing will saturate, and that's a little bit different than a lot of models. Is there anything else we want to say about ammonium? Okay, let's look at this. Let's look at this for a minute, just to show you. This is the kinetics, if you will, of ammonium. So all of this stuff in the all of this stuff in that square bracket is the influence of phytoplankton on ammonium. And you'll notice that what happens is in the front of it, we have our old friend, that ANC, you know, the nitrogen to carbon ratio, okay? Because, you know, the phytoplankton are quantified as carbon, but what we have to do is convert whatever happens to the phytoplankton carbon to whatever happens to the phytoplankton nitrogen. So, for example, you'll see here, we'll try to go over some of these. Basal metabolism, all right, so the ammonium is the basal metabolism times this thing, FNI. FNI is the fraction of metabolism that goes to inorganic nitrogen. Okay, so we have a metabolism times these two, BM times B, that's how much carbon goes into metabolism. And then we have something you're going to specify, FNI, which is of that, how much goes to ammonium. How much metabolism goes to inorganic nitrogen, ammonium. And that's a model parameter. And then what we've got here is, so that's a plus. Ammonium goes up, metabolism creates ammonium. Then you've got a minus here. This PN is the ammonium preference. This says P is production. It could also be growth times the algal biomass. So ammonium is taken up by production. And then you've got another positive, another source, which is predation, and this is FNIP. That's the fraction of the algae that is lost to predation, what fraction goes to ammonium. So these are things that you are going to specify. The FNI, the fraction of algal metabolism that goes to ammonium, and the FNIP, which is the fraction of predation that goes to ammonium. And then you've got, you know, simple enough, the dissolved organic nitrogen, the mineralization constant times DON, and this is nitrification over here. But the main thing I wanted to get to you is sort of how we handle these two fractions, these distribution coefficients, if you will. Kyle, go ahead, please.
Thanks. Are FNI and FNIP also specific to each parameter and also geographically different?
Potentially they differ. All right. Potentially the FNI differs by algal group. I don't think we allow it to vary geographically. Okay. So it can vary by group. And I think the predation does not, but I'd have to look. I think the predation just is. Let me see. Is there anything else I want to go into there? Just by analogy, if you will, here, for example, this is dissolved organic nitrogen. And once again, what we've got is metabolism times algal biomass. Now we've got an FND. So what fraction of metabolism goes to dissolved organic nitrogen? And we've got predation, FNDP. What fraction of predation goes to dissolved organic nitrogen? And I won't go over them, but you've got them for G1, G2, G3 particles. So just to reiterate, these are things that you're going to want to specify.
So, Colin, do you know if anybody is actually measuring these distributions? It's
the devil. It's the devil, I don't know where I'd send you, really, it's tough. Take a phytoplankton and a zooplankton and put them in a cage and try to measure ammonium production, but you don't really know, did that ammonium come from the algae? Did it come from the zooplankton? Where did it, you know what I mean? It's a really difficult thing to measure. So I'm going to say the best thing you can do is look at a lot of models and get a feeling for what the numbers are. Okay, so now we're on to phosphorus. And I think we go up here. There were two things. Phosphorus, okay. There were two things I really wanted to do before I finished my career. One was a wetland model, and one was a good phosphorus model. And we've started on the wetlands, but I never got to the phosphorus, so I'll leave that to somebody else. But meanwhile, we'll cobble together the phosphorus that we've got here. The soapbox. I'm up on the soapbox. Most models, including this one, will treat phosphorus analogously, is that a word? Analogous to ammonium or to nitrogen. They're really very, very different. And the more, a place like Chesapeake Bay, trying to model phosphorus is extremely vexing. And I may talk a little bit about it or I may not. But for the moment, what we're going to say is that once again, as with the nitrogen, if it's got a box around it, it's a model variable. And as with the nitrogen, there's no open arrows. We are meticulous about balancing, keeping mass balance on our phosphorus. Dissolved phosphate, in one sense, is analogous to nitrate and ammonium in that it is the nutrient that is taken up by phytoplankton. Now, we don't have to worry about a preference because there's only dissolved phosphate. There's not nitrate and ammonium, so we don't worry about a preference. Algal mortality, the respiration plus the predation, distributes it to a dissolved organic pool. Our three particulate organic groups are G1, G2, G3, and also back to dissolved phosphate. So once again, you have 5 options for how you distribute algal mortality. The particulate organic groups undergo hydrolysis, dissolved organic phosphorus. The dissolved organic phosphorus undergoes mineralization to phosphate. We have also another phosphorus variable which doesn't have an equivalent or an analog in nitrogen, which is particulate inorganic phosphorus. Okay, this in our representation is a distinctive phosphorus, a distinctive substance. And it abundantly comes into the bay from the watershed. I won't go on the soapbox, but I'll put it this way. A lot of models represent particulate, they sorb phosphate to solids. And in a sense, you could call that particulate inorganic phosphorus. We do not sorb. This is a mineral form, apatite potentially. It could be an iron compound. It's something that actually is very refractory. It's rock. But if you take that rock and you boil it in acid at a high temperature, you'll get phosphorus. So you want to get phosphorus, you got to boil it in acid at a high temperature. If you just put it in water, you have a long wait. But We do, at least in model world, we allow particulate inorganic phosphorus to dissolve and to dissolve phosphate. So there's a parameter in there. If you want to dissolve it, you can. You can also settle it into the sediments, okay? And one of my frustrations truly is I wish I knew more about particulate organic phosphorus, inorganic, and I'd love to really parameterize that dissolution properly. Okay, but I didn't, and it's too late now. Okay, where are we?
Quick question, Carl?
Yeah, go ahead, Jim.
Just thinking, I think, conversation last night, the model has that dissolution process, but I thought you said that in the Bay model, you don't allow that to occur.
In the Bay model, that parameter is set to 0.
Okay. And that's largely, because to a degree, is the PIP that you're having coming from the land side, not so much from the watershed per se, that may have been driving initially. Was it more of the runoff that's sort of eroding from the banks, or is it?
The bank is a big source of it.
Okay.
Although it's interesting, Jim. I may have the figure. I may have the figure here. I may not. 40% of the particulate phosphorus that comes over Conowingo is inorganic.
Okay.
So it's a big.
it is still a big
it's
part.
big in the watershed. Yeah.
And then that PIP just goes into the PIP variable in the
Sediment.
plus model.
And it is subject to.
Some of it can come back,
Yeah.
but only through the sediment.
That is correct. In our representation, that is correct.
Okay.
So there's no absorption, desorption for the dissolved?
No. And I can tell you, again, I don't know if I have the figures here. I have tried countless times. The Bay program has a wonderful data set of PIP, larger because I told them they need it. But, you know, you can plot and they have a wonderful data set of suspended solids, inorganic solids, and they have a wonderful data set of DIP. And if you manipulate those and plot them and try to see that it sorbs and desorbs, you won't. I've never seen it. You know, so in fact, the kinetic parameters to have sorption of phosphate to solids are in the model, if you wish to do that, but I've set them so there's no sorption, desorption. Gary?
So just to bring in the watershed perspective a little bit, it's the same type of thing in the watershed, but we are calibrating to observations that are total phosphorus and then dissolved inorganic. And so everything else is lumped into, in terms of observation, just essentially everything else. And so the PIP versus organics are not really well understood from the observation data set. We also have that same process where we've got PIP and dissolved phosphate, and there's an instantaneous partitioning coefficient. So in the watershed side, they do move back and forth. If you dump dissolved phosphate in from a point source, the next hour, there's going to be some amount of that's PIP based on the amount of sediment that you have, of fixed solids that you have. And so it's not all rock essentially coming from the watershed, at least in the way that we're simulating it. Some of it, I guess, from my mind, the watershed should have that process. But again, it's not really well understood in the watershed, and I like that you're encouraging everybody here to investigate it, because I think that's needed.
To really do to really do it right, we need an iron model, and you know now you got a real data shortage, and that's part of the frustration. Jim,
Does PIP have a pretty high selling rate compared to, let's say, algae?
I think it's actually kind of low.
It's kind of low. Okay.
It's kind of low, yeah. Okay, let's see where we stand here.
Otherwise, it would settle in the shallow, so you
Yeah.
let it distribute a little bit more. Okay.
Yeah.